Number 7, what's the probability of getting at most 3 correct? What that's talking about is the probability that x is going to be less than or equal to 3. So there's a couple of ways to handle this. One would be based off the table that we, just created 24 hours ago. But what we could do is we could actually take our answers for the probability of getting 0 correct, 1 correct, 2 correct, 3 correct, and add them all up. All right, those would be the specific instances in which you're getting the desired number of values correct. All right, so that would be the same as saying the probability of x equals 1 plus, x equals 0, plus the probability of x equals 1, plus the probability of x equals 2, plus the probability of x equals 3. All right. So we could take all those decimal values and add them together. All right. So it'd take a little doing, but, and there'd be some variation because we put our answers for the most part in decimal form, but there's tabular approaches that you could take, but there's a better way to do it, and that involves this new function. We used Binomial PDF yesterday. We're going to use Binomial CDF today. Yeah, Luke, what's up?
So like with this question, I see how you're like writing it out, but like how, I guess like I'm assuming what you're going to do is add up the 4 values.
That's one way to do it, yeah.
Like, how would we know if they're asking us to, like, show out the complete work of the equation or just add up the free?
So how do we know to write it like this explicitly versus just add them up and give an answer?
Like, how do you know if it's, like, okay to just add the 3 values that we already found up, or, like, opposed to, like, actually putting 3 into the equation?
Putting
like
3.
How do you know when you have to evaluate it with the formula opposed to just adding up the values you already found?
So I would assume that for any free response question, you're going to have to use a formulaic approach in all circumstances.
Okay.
Yeah. It's when you get the multiple choice questions, that's when you just say, I'm just going to chuck it in and crunch some numbers. All right. So what we would do here is we would take our 0.237. We would add to that the 0.396, the 0.264, and the 0.0879, and that would give us a reasonable approximation of the correct answer. There might be some slight variations due to rounding, but since we use the appropriate rounding convention for each individual probability, we would get an acceptable answer when we add up all those values. All right. Provided, of course, I type it in correctly. But we're looking at 0.985-ish. All right. So that's one approach. The other approach would be to use Binomial CDF in the calculator. But remember what I was saying yesterday, the AP folks, or at least I kind of implied it. I don't know if I ever actually mentioned the AP, but we don't want to write things in terms of calculator speak. We want to use the appropriate notation. And then the calculator hocus pocus can happen behind the scenes, but we still need to use the appropriate notation to come up with the solution. All right, so you could arrive at this answer using a function in the calculator, Binomial CDF. That's the cumulative density function. So second vars, option, I believe it's A. No, it's B. All right, and the old TI-83s, I think it was B. I'm sorry, A. But they threw in some chi-square stuff in recent years. All right, so Binomial CDF is the one you want. That's a cumulative density function. See, it's very easy to confuse that with Binomial PDF. PDF is for a particular value. I mean, the P doesn't stand for particular, but It's a probability density function. The cumulative density function gives you probabilities over an interval. All right. So when I hit enter on that, you see, unfortunately, it has a similar setup. I'll go back to Binomial PDF real quick. Second vars is what I meant to hit. Second vars option. It was the Binomial PDF. You see it's trials, the P and the X value. Now if I do Binomial CDF, trials, P, and X value. So if you select the wrong one, it's not going to distinguish itself. You're going to look at it and say, oh, I must be in the right one. It looks the way I expected it to look. All right, but the trials here, well, we still have the 5 questions. The probability of success was a 1 in 4. Now that X value here represents the most number of successes. All right, so I'd put a 3 here. That X value for Binomial CDF is the most number of successes that you'd be interested in over an interval. All right, so this is from 0 to whatever your X is. 0 to whatever your desired X value is. Nice. As opposed to Binomial PDF, where it's just at the X value, the desired X value. All right, so that's where one way that we could come up with all these values, but here it's going to give us an interval from 0 to whatever that X value is, in this case 3. All right, so the number of trials, 5, probability of success, 1/4, 3, at most 3 successes, paste it in. Then, what I wrote down on paper looks a little different from what the wizard, they call it the wizard, looks like, but it ultimately pastes it in the appropriate fashion. And you see we come up with the same probability, or roughly the same probability. Again, acceptable variation due to rounding. All right, so that's not bad, provided you know how to navigate the calculator. All right, so you could just jump right to the correct answer. The problem is, if it's a free response question, you got to give me more than that. All right, in order to get full credit, you have to show all this stuff. That's why I'm saying, like, the whole AP process is so archaic, because they're kind of latching on to the old way of doing things, but we have this new, well, quote unquote, new technology that'll do all this stuff for us, but they don't want to let go of the old ways. All right. So what we have to do is sort of kind of navigate around that. Like, for example, in number 8, when it says what's the probability of getting 3 or more correct, I got to be thinking, all right, if we have 5 possible outcomes, well, really 6 possible outcomes, because you could get none right. So 0 or 1 or 2 or 3 or 4 or 5. 3 or more would be this set of outcomes. All right, so I would want to be thinking, all right, what's going to be more efficient? Finding the probability of 3, finding the probability of 4 or 5 correct, adding them up, or finding the probability of getting at most 2 correct and subtracting that from 1. All right, but the thing is, we still have to show the work. All right, so what I would do is I would find 1 minus the probability that X is less than or equal to 2, which would be 1 minus the probability that X is equal to 0 plus X is equal to 1 plus the probability X is equal to 2. All right, with the hideous double parentheses there. All right. So then I would pop those values in, which I already have. So 0.237 plus 0.396 plus 0.264. But again, it's kind of about, or more about being efficient. You'd look at that and say, okay, well, what is the sum of these 3 values? It's really just my previous sum, the 0.985, but just knock off the 0.0879. All right, so it's just a quick subtraction. All right, and then take that result and subtract it from 1. All right, so 1 minus the sum of these values, again, if you're just doing it all out. But then once you get to this step, you don't actually have to do what I'm doing here, because you could do that work behind the scenes. It's the calculator hocus pocus. We're talking about an answer roughly about 0.103. All right, so what I would do instead is 1 minus, then I'd go into second vars binom CDF, 5 trials, probability of success 0.25. The most number that I would want to have correct, the most number of correct answers. And then get my answer that way. Right? Slight variation due to rounding, though. Right? So it may not jive 100%, but that's okay. All right. So 0.103, 0.104 in that neighborhood is what we're looking at. It's again, it's just trying to reconcile what they want and what we're allowed to do behind the scenes. All right? Because they want the notation. All right? We want to show nothing. We want to give the answer, and that's it. So this is kind of like that middle ground. All right? So what I usually would do on a test, and you know, like I don't have a hard fast rule one way or the other, but I usually just kind of let people get away with stopping here and then going right to the answer. You know, not showing all this stuff, because I feel like that's definitely a waste of time. You know, especially if we all know you're going to do it behind the scenes in the calculator. So that's kind of where I'm at with it. But those AP folks, they just make up their rules as they go, and most of the time they don't make any sense. Right, so it is what it is. But we'll talk about all the different ways to make sense of the nonsensical as we get closer and closer. All right. But the one last thing that we wanted to talk about, or at least in this topic, is finding mean and standard deviations. That it might be like, oh, we've already done this, but there are shortcut rules, and I won't bore you with the proof at this point, but you could find the mean and standard deviation of a binomial distribution, assuming that you know the distribution is binomial by nature, and we know that that's the case if it satisfies the 4 conditions necessary to be binomial: fixed number of trials, fixed probability, independent events, and 2 outcomes. All right, you want to be able to rattle off those 4 conditions off the top of your head. All right, so that's important. And I always put a question like that on the test when we do take a test eventually. It'll be, what are the 4 conditions necessary for a distribution to be considered binomial? It's usually question 2, if anybody was wondering. But, you know, sometimes it's question 3. But those are the 4 conditions: fixed number of trials, fixed probability, independent events, and 2 outcomes. All right. If you know a distribution is binomial, then you could use the mu equals np and sigma equals the square root of npq shortcut formulas. I said npq. Q is equal to 1 minus p. So sometimes as a shorthand way of referencing it, they'll say the square root of npq. All right, they mean the same thing. All right, so if you ever see that, they're referencing the same formula. All right. So when I say recompute the mean and standard deviation using these new formulas, all right, it's related to the original scenario, which was, all right, the number of trials was 5. The probability of success was 1/4. All right. So mu would be equal to NP, which in turn is equal to 5 times 1/4, which is 5/4, or 1 1/4. All right. That's the expected value. All right. Remember, the mean of a probability distribution is also known as the expected value. So the number of questions that you could get right that's closest to this value is what you would expect to typically get right. You know, so again, a 5-question multiple choice assessment in which a person is making random selections for the answers, no studying, not even looking at the questions. And it's just like, You came into class late. You had 20 seconds before the end of class. The teacher is like, no, you got to take it right now. I've had enough of your guff. Just sit down and take this assessment. You only got 20 seconds to do it. You're like, well, I guess I might as well just guess. So boom, 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 and there you go. You don't even look at the questions. All right. So the expected value would be 1.25. So the closest integer value to that would be 1. You would expect you're going to get around one question right. All right. So the standard deviation would be the square root of np times 1 minus p, which is the square root of, well, really 5/4, but I'll write it out again. 5 times 1/4. 1 minus 1/4 is 3/4. So 5/4 times 3/4 would be 15 sixteenths, right? All right, we can go to decimal form for that. I guess we can go to decimal form for both of them. 1.25. And then the square root of 15 sixteenths. No need to rationalize denominators or anything like that. 0.968. All right. And those are the values that we came up with when we created the probability distribution from the table that we generated using the binomial theorem. All right. We used the calculator to come up with the mean and standard deviation, 1.25, 0.968. The benefit of this technique is that you don't need to have the entire distribution in order to determine the mean and standard deviation. All right. And so we can answer follow-up questions, the usual, unusual intervals. We can get at solutions to those problems too. So that's kind of nice. All right. So number 10 gets at that idea. Would you consider 68 correct answers on a 100-question multiple choice test with four choices each to be unusual? Right. So it's the same general theme. We have number of trials is equal to 100. Since it's the same general theme, we know that it's going to be binomial. Fixed number of trials, 100 questions. Fixed probability of a 1 in 4 chance of getting any question right. Independent events, we're at liberty to use choice A over and over again as much as we want. All right, so just because you use choice A once doesn't mean you can't use it again. So independent events, 2 outcomes, you're either going to get it right or wrong. Multiple ways to get it wrong, but still only 2 possible outcomes, right or wrong. All right. So mu would be equal to NP, which would be equal to 100 times 1/4, which is 25, which is, again, the expected value. And in this case, it kind of lines up nicely with what you would actually probably expect. You have a 1 in 4 chance of getting any question right. You answer 100 questions, you're probably going to get about 1/4 of them right. All right, on average. All right, so sigma would be equal to the square root of n times p times 1 minus p. So, or n times p times q if you want. But that's going to be 100 times 1/4 times 3/4. So that's the square root of 300 over 16. All right, so square root of 300 over 16, about 4.33. All right, so in order to determine usual or unusual, I want to compute mu plus or minus 2 sigma. All right, so mu minus 2 sigma, mu plus 2 sigma is going to give me the usual interval. All right, so that's going to give me 25 minus 2 times 4.33, 25 plus 2 times 4.33. All right, so we crunch a few more times, a couple more times, times 4.33. That's the low bound. Second enter. Change a minus to a plus. Upper bound. Our usual interval is anywhere between 16.34 and 33.66. So that's the neighborhood of the usual values, all right? So if I'm going to take a 100 question multiple choice test cold, no studying, just randomly guessing, I can expect, without raising any eyebrows, to get anywhere between or roughly 16 and 33, 34 questions right. So you go in, you take a quiz, a 100-question quiz. The teacher's looking at you being like, you haven't done anything all year. And then you rock like an 80 on it. They're expecting you to get somewhere between 16 and 33 questions right because they don't think you studied at all. And you got an 80. What's their thought? How'd you cheat? How'd you pull this one off? Because you haven't done anything. Like, okay, where's the cheat sheet? You know, now they're like staring at you during the test. That's always a good feeling too. I used to enjoy that one. So, but yeah, that's a nice application of a concept like this. So 68 would be unusually high. So if a student got a 68, the teacher is suspicious because they think the student isn't studying. All right, and they rocked a solid 68, and they're like, how'd you do that? All right, so long story short, 68 is unusual, but there's a lot more to it than that.
Is